this section of the class, we're going to talk about derivatives of trig functions, trigonometric functions. That means sine, cosine, tangent, secant, all those things that you learned from your trig or your pre-cal. Now, I'm not going to spend a lot of time deriving this stuff. You can look in your calculus book and it tells you how it's derived in all its excruciating detail. My goal is to tell you which identities, which derivatives you need to know for your problems, and then to go ahead and work some problems so that you'll know how to use them. So let's just go right into it. On the right hand side of the board, I'm going to go ahead and write some derivatives that you're going to need to basically memorize. And then we'll go ahead and I'll derive one of them for you to show you kind of what's going on, and then we'll work some problems. So remember, there's basically 6 trig functions. There's sine, cosine, tangent, and then there's cotangent, secant, and cosecant. So these are all cyclic trigonometric functions. We're gonna have the derivatives of those defined here. So I'll just say that the derivative with respect to x of sine of x, derivative of sine of x with respect to x, is equal to cosine of x. Okay? So the derivative of sine is cosine. The derivative of cosine is just simply negative sine x. So you see, these are kind of cool already because, you know, derivative of sine is cosine and derivative of cosine is negative sine. So they're opposites of one another. It's just that you have a negative in there you have to remember. The derivative with respect to x of tangent x is just equal to secant squared. Okay? And the derivative with respect to x of cotangent is equal to negative cosecant squared. And the derivative of secant is equal to tangent x times the secant of x, tangent times secant. So this is a multiplication here, tangent of x times secant of x. And then finally, the derivative of cosecant is equal to negative cotangent cosecant. Okay? And again, there's a parentheses around here. So you're taking these two quantities and you're multiplying together. So I know it looks a little bit crazy here, okay, and it's going to seem a little bit crazy at first because we haven't derived squat here. I'm just showing you what the results are because the point here is for me not to derive everything. The point is to learn how to use this stuff. There is a little bit of symmetry here that you'll see, and you can kind of just see it by reading. Derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of tangent is secant squared. Derivative of cotangent is negative cosecant squared. So you see, if you write it in this order, you've got a negative here and a negative here, and you'll see you've also got a negative here. And this is secant squared and cosecant squared, so there's a little bit of a symmetry there. Derivative of secant is tangent times secant. Cosecant is negative cotangent times cosecant. So if you say this list, you know, about 10 times, you'll start to just remember it, okay? Now, don't forget, what does a derivative mean? Okay, I'm not gonna go into a lot of detail, but you remember what the graph of the sine function looks like? Looks like this, okay? And this is 2 pi right here. So over 2 pi radians, it has one complete cycle. What this means is that the derivative is the cosine function, right? Which looks something like this. So that means that this is the sine function, and this is the cosine function. So that means at every point along sine, the slope of this line tangent to the curve, which is what the derivative is, you just have to come down here to the cosine and you'll see it. And when you really look at it, look, the sine function is pretty steep right here around 0. Okay, right along here, this is pretty steep, right? Right there. So the slope is pretty high. And that's why, if you look at the same value of x, you've got the maximum here in cosine. So the slope in this case is 1 because here in the cosine graph, cosine starts up at y is equal to 1 and goes down. Okay? So, but it's a maximum value. Now, as you go up the curve in sine, eventually you'll get to a plateau here where if you look at the line tangent to the sine graph up here, it goes right across the top. So the slope here is 0 because the slope of the line tangent to the curve is 0. Well, I haven't really lined up my drawings very well, but that's exactly what I'm trying to represent here. If you really want to look at it a little bit more closely, this is what it would look like. You'd have it going down like this, up like this, and over. Okay? So here, at this point, the slope of the line tangent to the sine curve is 0, so the derivative of sine, which is cosine, is 0 at that point. So this curve here, the cosine curve, is the derivative of the sine curve. Every point along the cosine curve is the slope of the line tangent to the sine curve. Okay, so what we're going to do is use this information to go ahead and calculate some derivatives, and I'm going to show you how to use this information here that you're going to end up memorizing as time goes on and actually working some problems. Before we get going with that, I thought it might be useful. Now, I'm not going to prove all of these things to you because, like I said, that's given in your book and that's pages and pages long. But I thought it might be instructive to show you at least where one of these things comes from. So I'm going to do that right now. Let's say that we want to take the derivative of tangent. And in the end, we're going to see it's going to be equal to secant squared. But the question is, how? Okay? And this could be the kind of thing they might ask you on a test. Well, I'm going to show you that really you have within your power at this very moment the capability to do this. And most of these, in fact, you could do this by yourself right now. But let's see how this is. If you remember back from your trig, the tangent function is simply defined by definition as the sine of x over the cosine of x. That's a definition. This is something that's just true. It's not anything I'm proving to you. That's what tangent is equal to. So what I need to do is take the derivative of a function that is a function of x divided by another function of x. Now, if you remember, when you have, just from in the section before, if you have a function of x divided by another function of x, this is like f of x, and this is g of x, and these are different functions, then it's the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. And so that's what we're going to do. We're going to apply this formula that tells you how to take the derivative of two functions of x divided by each other, and we're going to use that. So let's do that right now. The bottom is cosine, okay, times the derivative of the top. Okay, so the derivative of sine is cosine. Okay, you're just going to have to, believe me there and use some of the identities that are given and laid out before you. Bottom times the derivative of the top. Derivative of the top is cosine minus the top, which is sine of x, times the derivative of the bottom. The derivative of cosine is negative sine, so it's going to be negative sine here. And all of this stuff is divided by the bottom squared, cosine squared x. So just take a moment and make sure you're with me up to this point. Bottom times the derivative of top minus top times the derivative of bottom over the bottom squared. Bottom times the derivative of the top, derivative of sine is cosine, minus the top, which is this, times the derivative of the bottom. Derivative of the bottom is minus sine of x divided by the bottom squared. Excellent. Now I'm going to get rid of this. We don't need this anymore. We've used that formula. Now all we have to do is simplify this. Cosine times cosine is simply cosine squared of x. This is the same way of writing cosine of x squared. You could simply write it like this, but you'll see frequently in calculus when you're dealing with trigonometric functions, or even in trigonometry, when you square something like this, it's just more convenient to write the square here, and you just know that what this means is simply the cosine, evaluate the cosine, and then take that and square it. If it's cosine of x to the 6th power, well then that's cosine to the power of 6 of the variable x. I just want to quickly make sure you understand that. So cosine squared. Now I have a minus and a minus, so that's going to be plus sine squared of x, all divided by cosine squared of x. Now the top here should look familiar to you. That's a big, big fundamental identity. Cosine squared plus sine squared of any argument, and the argument here is the same, it's x, is simply 1. You can go look that up in a table of trig functions. Cosine squared plus sine squared is 1. That is one of the few identities in trig that you actually need to really remember. In the bottom is still cosine squared x. Now, you can write this as simply 1 over cosine of x all squared. Now, just make sure you're with me here. What I've done here is I've pulled this square and I've made the whole thing squared, and that's true because here, if I were to square the top, I get 1. 1 times 1 is just simply 1. And then if I square the bottom, well, then I have what I started with. So I just wrote it on the outside. And the reason I did that, I'm going to show you a little aside here. If you pick up my DVD course in trigonometry and pre-calculus, you'll see an entire course of the neat things to remember to help you do well in this stuff. But just suffice to say, if you write down your trig functions in this order, sine, cosine, tangent, cotangent, secant, cosecant. So you just write them in that order, sine, cosine, tangent, cotangent, secant, cosecant, and you draw what I like to call a little rainbow, like this. Then it's easy to remember that 1 over cosine is equal to secant. What this little table is telling you is sine is 1 over cosecant, cosine is 1 over secant, tangent is 1 over cotangent. Likewise, cosecant is 1 over sine, secant is 1 over cosine, and so on. So whichever thing you start with over here is just equal to 1 over whatever's at the end of the rainbow over there. That becomes very, very useful. You notice I didn't look at any table of trig functions. I just happened to, and I don't have all these memorized. I just write it down and figure it out. But you could also look in a table, and you could convince yourself that 1 over cosine is equal to secant. So then what you get in the end is secant squared of x. And that's exactly what we started with. So we've proved that the derivative of the tangent function is equal to secant squared of x. And you can do this kind of thing with any of these, and it's a pretty common test question if you get there. You know, when you get to taking your test on derivatives, prove that, you know, or show that the derivative of tangent secant squared, or that the derivative of cosine is this. You can actually, these are kind of fundamental. You won't really be able to prove these, but when you get into these, you can do some tricks to help figure those out. Let's work some problems. I want you to take this as fact, and it is fact, and that's something that you'll end up memorizing. And we're going to use that information to take some derivatives. So what if you have sine of x plus cosine of x, and we want to find the derivative? Well, the derivative is y prime, and we're going to start easy and we're going to get a little bit harder. When you take derivatives, if you have things added together, you just take the derivative of the first thing, and then you can take the derivative of the second thing, and you add them up. Derivative of sine is given by cosine. Okay? The derivative of cosine is given by negative sine. Okay? And so then you'll just say on your test or your homework that this is equal to cosine of x minus sine of x. Very, very simple, okay? I mean, we didn't do anything magical here. I just said take the derivative, and I'm giving you a table of common derivatives, and you just kind of use that. The one thing I want to point out to you that you might want to do as you go forward is you notice how I didn't cut any corners here. When I wrote the derivative of the first term, I put my plus down, and then I said, okay, now the derivative of cosine is negative sine, and I put that quantity in parentheses, and in the next step, I pulled it out and I put the minus sign in between them. You know, if you're clever, you can just skip this step entirely and go straight here and put this minus sign here, and you might end up doing that. But I recommend in the beginning that you take it slow. Don't try to save one line. Write it very explicitly so that you don't miss a sign error, because you will miss one. It's just a matter of time. What if you have cosecant of x plus, actually what I want to do is something a little bit more challenging. Cosecant of x times the cotangent of x, and you're supposed to take the derivative of that. Okay? So the derivative is equal to, again, you should remember from the other techniques of taking derivatives from before that if you have two things multiplied together and you're trying to take the derivative, and when I say two things, I mean two functions of x, like here's a function of x and here's a function of x, then it's just the first times the derivative of the second plus the second times the derivative of the first. It's just something you'll end up memorizing, and we've already worked some problems that have used this. The first thing is cosecant of x, so I just write it down again. No big deal. And I'm putting parentheses here to make sure I'm very clear what I'm doing. Times the derivative of the second. Derivative of cotangent I have written down right here as negative cosecant squared of x. First times the derivative of the second plus the second, which is cotangent, times the derivative of the first, which is derivative of cosecant. Derivative of cosecant is this stuff. And so what I'm going to have here is I'm going to have negative cotangent x cosecant x. Okay? So we don't need this anymore. We've used that property. I just wanted to write that down for you to refresh your memory. And as we work problems, you will end up memorizing it. So all we did was we used that property first times the derivative of the second term plus the second term, which was this one, times the derivative of the first term. Derivative of the first term happened to be this mess because I just gave that to you right there as a given. So now we just simplify. The derivative then reduces to negative cosecant x. Let's write it like I just showed you how a minute ago. Negative cosecant x to the third power. That means multiplied by itself 3 times. Okay, and then over here I'm going to have minus, because of this minus sign here, cotangent squared x times cosecant x. And you can put parentheses here to keep it all straight, like this. Okay? And that is going to be the answer. It's very simple. You see, you've got to keep your signs straight. And you might think, wow, geez, this doesn't look very simplified. Well, it's about as simplified as you can get. You've got a cosecant here. I mean, I could pull out a cosecant here. I've got a cosecant common, and I could factor it out. But is that really any more simple? Probably not. So I don't want to bother to do that. You may fret a little bit on how simplified you should make these things. And my advice is really don't worry about it. The main point is how do you apply the formulas to find the derivative? Simplification, I mean, it's great and all, but it's kind of a matter of perspective. Some people like it less simplified, and some people like it more simplified. So what if you have the tangent of x divided by x, and you have to find the derivative? So then the derivative of y with respect to x, this is the same thing as saying y prime. I'm just writing it 2 different ways to show you that you can. Well, you have a function of x divided by a function of x. So we're going to use our formula that you may or may not remember. Okay, so I'm going to have the bottom, which is x, times the derivative of the top. Derivative of the top is secant squared, minus the top, which is tangent, times the derivative of the bottom. Derivative of x is just simply 1. And remember, you take this because this is x to the 1 power. So the 1 comes out of the exponent, and you have x to the 0 power left over. So in the end, you're just left with 1 over x squared. Bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. And you just go and you simplify, which is actually pretty much already simplified. Okay, that's it. That's the answer. That's the answer. Really, the trick is keeping your signs straight and knowing which, in that case we had to use the division rule to take the derivative. In the other case we had to use the multiplication rule. Really, we're exercising the same rules. We're just doing it with trig functions instead of with just simple polynomials. Okay, so in this problem, we have sine x and cosine x in the bottom, and we have x in the top. But you see it's the same form as the last problem. We've got a function of x on the top and a function of x on the bottom. And so we have to use the same technique. We have to use our division rule to take the derivative of this. So we have and I'm just going into more and more complicated problems to show you that it's the same thing. And that's what I mean. Calculus gets a bad rap. It seems like, oh, it's so hard. Really, calculus is just tedious. Once you know a few simple rules on how to actually take the derivative, it just becomes a matter of turning the crank to actually get it done. And sometimes turning the crank can be a real pain because the problems can get really complicated. But let's just do this. We're going to use the division rule to take the derivative. So we have the bottom, which is the sine of x, plus the cosine of x, times the derivative of the top, which is just 1, derivative of x is 1, minus the top times the derivative of the bottom. Derivative of sine is cosine, and the derivative of cosine is negative sine. And then the whole thing is going to be divided by the bottom squared, which is sine x plus cosine x squared. So you have the bottom times the derivative of the top minus the top, which is this, derivative of the bottom. You just take the derivative of each term. Derivative of sine is cosine. Derivative of cosine is negative sine. And here I have a plus minus, and that's going to turn into a big fat minus there in a minute, but I just want to keep everything explicit so you know where everything comes from. So we have sine x plus cosine x, that takes care of this stuff, minus x times the cosine of x plus x times the sine of x. Okay? And on the bottom, we're going to have sine x plus cosine x squared. Okay, and so that's basically the end of that problem. You could try to do some more simplification, pulling out sines and cosines, and you could cancel a little bit of the denominator, but you're not going to be able to cancel the whole thing. So this is about as simplified as it gets for this guy. The real trick is just learning how to use the formulas for the derivative. What if you have x to the minus 3 power times sine of x times tangent of x? Okay? Then the derivative, the derivative, y prime. Well, now this may look a little bit weird because you have 3 terms. So what do you do here? Well, my advice to you is, since your the rule that you know of so far to take a derivative of 2 things multiplied together would look like this. First times the derivative of the second plus the second times the derivative of the first. That's what we've been working with. My advice to you would be to treat this as 1 term and then treat this as 1 term. So this is your first function here, and this is your second function here, and you will see that that's going to help you. So the first term is just x to the minus 3 times sine of x, okay, that's a term, times the derivative of the second term. Derivative of tangent is secant squared, okay, plus second term is tangent of x times the derivative of the first term. Now, the way I'm going to write that is just x to the minus 3 times sine of x, and I'm going to put a big mark here that tells me I have to take the derivative of that. So here's the first term times the derivative of the second, we got that from here, plus the second term times the derivative of the first, but I actually haven't taken this derivative yet. Okay? We have to do that now. Okay, so what we want to do now is work with this term and find the derivative of that. So we've got the first term here is x to the minus 3 times the derivative of the second. Derivative of the second term is just cosine of x. First times the derivative of the second plus the second, which is the sine of x, times the derivative of the first. And this is a polynomial, and remember the way you take the derivative of that is minus 3x to the minus 4. The exponent comes out in front, and then you put x, and then you subtract 1 from the exponent, and that leaves you with that. So really, we're applying the same rule, but we're doing it inside here. So this times the derivative of sine will give you this, plus the derivative of this times I'm sorry, plus this times the derivative of this, which is what gives you that there. So in the end, this term will be x to the minus 3 times cosine of x minus 3x to the minus 4 times sine of x. Okay? Which will give you basically this term right down there. So, to rewrite all this business again, what you'll have is x to the minus 3 times sine of x times secant squared of x plus tangent of x, and then you'll be multiplied by all this stuff here, which will be x to the minus 3 cosine of x minus 3x to the minus 4 sine of x. Okay? So in the end, really all you're going to have is you can distribute this tangent in, and that's about all you're going to be able to do. So you have y prime is equal to x to the minus 3 sine of x secant squared of x plus, and then I'm just going to distribute this tangent in, x to the minus 3 tangent of x cosine of x, that's tangent distributed into this first term, minus 3x minus 4 tangent x sine of x. So this is the tangent distributed into the second term. And really that's the answer. I mean, it's completely nasty, yes, I agree with you, but this is the answer, this big old thing right here. And it doesn't look simple, but sometimes, you know, things don't look very simple. That's going to be a theme you'll see kind of throughout calculus, is that sometimes the answers really don't look all that terribly simple. Now, I just want to quickly review what we did in this particular problem, just to kind of make sure we're all together here. We had a first term that we defined and a second term. We used the multiplication rule. We said this times the derivative of the second term plus the second term times the derivative of the first term, but initially we just left it like this. You could have just taken the derivative right inside of here if you want, but for clarity I left it like that. Then we went down to the bottom and we figured out that the derivative of this was just equal to this stuff down here. First term times the derivative of the second term. First term is this one times the derivative of the second term gives me the cosine, plus the second term is the sine of x times the derivative of the first term gives you this 3x to the negative 4. The negative sign comes from this negative 3 up here. So this term is the derivative of that second term, and then you just distribute this tangent in, you get 3 very ugly looking terms. But that's the answer. We'll do one final problem in dealing with trig, taking derivatives of trig functions. And I don't want you to lose sight of the big picture here, okay? Never lose sight of the big picture. The big picture is that the derivative of a function is just simply a representation of the slope of that function as you trace along its path. So everywhere you go on the path, the derivative tells you how it's sloping, if it's steep or if it's not so steep. You know, we're getting very complicated looking answers, but if you were to go to a computer and plot the original function and then plot the derivative, you could figure out and look at it and see that the derivative is just telling you the slope. So it's a lot of mechanics you have to crank through to get to the derivative, but the big picture is just simply that, it's the slope. Okay, so the concept is not that terribly difficult. What if you had x squared times tangent of x over secant of x? Okay. Well, again, we've got a term in x and another term in x, and they're divided, so you have to use that division thing. So it's going to be the bottom, which is secant of x, times the derivative of the top, which I'm just going to write as x squared tangent of x, and I'm going to put a derivative mark here to remind myself that I have to take the derivative of that, minus, so the bottom times the derivative of the top minus the top, x squared tangent x times the derivative of the bottom. Derivative of secant is simply tangent times secant. Okay, so actually what I'm going to do here, since we ran out of a little bit of space, is I'm going to rewrite it here. Secant times x squared tangent x, got to take the derivative, minus x squared tangent of x. Now I've got to take the derivative of Bottom times the derivative of top minus top times the derivative of the bottom. So I've got to take the derivative of secant, which gives me tangent times secant. Tangent of x times secant of x, which is given right here. Okay? And then I've got to take the whole thing and divide it by the bottom squared. Secant squared. Okay? Now, what I need to do next is just go ahead and distribute this stuff in. And what you'll actually see very quickly is that, you see, I've got a secant here, and I've got a secant here, and this is all multiplied together, and I've got a secant squared on the bottom. So, if I were to factor out a secant on the top, both of these secants would come out in front of everything, and I would have a term left over. I've got secant squared on the bottom. So, what I know is that this secant cancels with, well, both of these secants cancel with only one of the secants on the bottom, and that's why I've just scratched out the 2, because I still have one secant left over. Now, just to recap, okay, what I did here is I basically, in one step, I've factored out a secant on the top, and then what I would have had left over on the top would be x squared tangent x, and I've got to take the derivative, and then over here I have x squared tangent times tangent, because I have a tangent here and a tangent here. And you can see that you can factor out a secant and from both of these terms, and so that's why I can write it here. Now, it was all over secant, essentially, times secant, because I had a secant squared. So I just scratched through one of these secants and scratched through one of those secants. So on the bottom, I have a secant left over. That was what I did in kind of in one step. I just want to show you where it comes from. So I've gotten rid of those secants. So what I need to do next as I go to the next step is I need to take this derivative. So let's do that. Let's take the derivative. It's multiplication, so I have to do it with the multiplication rule. So first term times the derivative of the second term. Derivative of tangent is secant squared. Okay, so now that's this times the derivative of this plus tangent x times the derivative of the first term. And the derivative of x squared, if you'll recall, is just 2x. The 2 comes down, and then x raised to the 2 minus 1 power, or to the 1 power. So I've got this times the derivative of this plus this, the second term, times the derivative of the first. So I'm good to go there. So this is this term expanded out because I've taken the derivative. And then here, I've got a minus, and I've got an x squared, and I've got a tangent times a tangent, which is a tangent squared of x, and then on the bottom, all I have is one secant of x left over. Okay, I've got one secant of x left over. So, in the end, really the only thing that you can really do left is, you see, I've got an x here, and I've got an x squared here, and I've got a tangent and a 2x here, and I've got an x squared here. So really what I'm going to do is I'm going to take an x squared and I'm going to factor out an x squared from here. So I'm going to have x squared, and inside of this I'm just going to have secant squared of x minus tangent squared of x. Okay, and you'll see where I'm going with this in a second. Plus 2x tangent of x. And on the bottom you still have the same old secant of x. Now that's almost the answer. What I did right here is this term, this one right here, and this one right here, these two terms, they both have x squares in them. So I just factored out the x squared, and what I had left over here was the secant squared, and what I had left over here was the negative tangent squared, because you've got to keep your negative there. And this term here in the middle I didn't do anything with, I just kind of left it over there. Now you might say, why in the heck did I do that? If you remember, there is an identity. You probably don't remember. I had to look this one up myself. There's an identity from trig, if you go and you look that up, that says tangent squared plus 1 is equal to secant squared. That's just an identity. So then you can convince yourself that secant squared minus tangent squared is equal to 1. Okay? Subtract tangent squared from both sides, and you're left with this bottom thing. Now look at what we have here. We have a secant squared minus a tangent squared. So everything in here is equal to 1. Just a flat old 1. So in the end, what you have is just x squared. You're multiplying by 1 here, so that drops away, plus 2x tangent of x over secant of x. And that's the answer. So truthfully, this was the answer here, okay? And if you left it like that, that's probably okay. It's just that this is a pretty big identity. If you happen to remember it, you can just strike through and basically simplify your answer quite a bit. So this is the answer right here.